Now that we know the numbers that stay clear in their own boundaries of rationality and irrationality, I'm going to introduce the ones that don't and can easily trick you into thinking their identities are opposite of what they truly are. And they're called infinitesimals. They're numbers that have numbers past the decimal point that goes on forever. I know some of you might be thinking right at this moment, because I've just said in my previous video, pi is a number that goes on forever and belongs in the irrational realm. All the other infinitesimals probably belong there too. However, it's only half true. Infinitesimals can be also split into two parts, just like the rational numbers and irrational numbers. First is repeating infinitesimals. Second part is, as you guys might have guessed, non-repetitive decimals. Repeating decimals belong in the rational number section, and I'll prove it to you. So you guys might be wondering, how can someone express a number that we don't know where it ends and goes it forever in a fraction form? Because we have no idea how long the numerator and denominator is going to be. However, if you have a number that has a part beyond the decimal point, that repeats and has a pattern that is easily predictable, we can see easily how the number is going to turn up in a fraction. For example, let's pick a repeating decimal like 0.7777 that has 7 to go on forever beyond the decimal point. And we can easily predict that the next digit is going to turn up after the thousandth of seventh, it's probably going to be 7 too. We can write 0.7777 that has 7 to go on for infinity. We can write this as 0.7 with a little dot on top of 7, or as 0.7 with a little line on top of 0.7, or 7 in natural. We can easily see how the next number is going to be 7. The 7 is the pattern. Or if it's number something like 0.231231, we can easily see the next number is going to be 2 and then 3 and then 1, which shows us that 231 is a pattern that we can simply guess. And we can write this as 0.231 with dots like these, or 0.231 with a single line like this. So in my previous video, I've explained to all of you how a rational number is a number that can be expressed in a fraction form, correct? Which means if repeating decimals are indeed belongings in the rational realm, that they can also be turned into a fraction form. But before I do that and prove it to you how it is a rational number, let me prove to you why non-repetitive decimals can never be expressed in fraction form. So pi is a very easy and simple main example of non-repetitive decimals because it has numbers beyond the decimal point that is not predictable, does not have a pattern, like 0.369, and then that goes on forever, that with a number that we cannot predict. Or with a number like 0.4321256 that we can see no visible patterns. They have no patterns that we can recognize, that we can see or think and say, oh, if this is going to be put into a fraction form, this is going to be the denominator and this is going to be the numerator. But how is it different for repeating decimal? Well, let's just give a very easy example and say 0.7 with a line on top that we previously talked about. And let's say I want to call this number x. So if I say x basically means 0.7 with a line on top that has 7 to goes on forever for infinity amount of time. So 7 is the pattern, and we can simply see how that is going to be turned up next. So if we say 10x, which is 10 times the x, it's going to be 10 times the 0.7 with line on top of 7, like this. So if I want to subtract x from 10x, it's going to have us to end up with 9x. And 9x is going to be equal to, because basically 10x is equal to 10 times 0.7 with line on top, which is going to give us 7.7 with line on top. And if we're going to subtract that 0.7 with line on top from that, we end up with just 7, because this infinity point gets to be erased because they're the exact same. And if you want to end up with an x at the end of the day, we have to divide both sides by 9, which have us to end up with this equation that x is equal to 7 over 9. So if x is equal to 7 over 9, but if x is also equal to 0.7 with a line on top, as we said in the beginning of this chapter, we can easily assume that x is also equal to this equation, which tells us that 0.7 with a line on top is equal to 7 over 9, which proves my theory and my fact that these repeating decimals can indeed be put into a fraction form and are indeed a part in the rational realm.